You're listening to the Future Tech Podcast with Richard Jacobs. Future technologies such as artificial intelligence, stem cells, 3D printing, gene editing, Bitcoin, blockchain, the microbiome, quantum computing, virtual reality, and exploring space are much closer than you might think. In fact, many early versions of these technologies are in play right now, and the companies that are using these technologies are the focus of this podcast. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a thorny medical problem. Remember, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you've enjoyed the podcast, please listen, subscribe, like, and tell your friends about it. Thank you. Hello, this is Richard Jacobs with the Future Tech Podcast. My guest is David Keith. He's the chief scientist and board member and founder of Carbon Engineering. The website is carbonengineering.com. So, David, thank you for coming.
Thanks. Great to be here.
Yeah, I had read the article where they talked about direct air capture to pull, I guess, carbon dioxide out of the air. Can we talk a little bit about that? How does that technology work, and what are some of the nuances of it?
Direct air capture is just the process of concentrating CO2, of taking in atmospheric air and having as the output a pure stream of carbon dioxide. Obviously, it takes energy and capital to do that. So the fundamental idea of doing it is old. There have been industrial processes that have done some version of air capture for a long time. For example, as a step before cryogenic air separation, if you want to make argon. But the idea of doing it as something relevant for climate to get carbon dioxide at interesting costs for direct air capture is a relatively new idea, and we're one of a couple of companies that have really kind of seriously pursued technology to bring that into the commercial marketplace.
Well, I don't know if people know, but what are the uses of pure carbon dioxide? I mean, it's great if we can get it out of the air, but how is it used industrially?
I can tell you that, but I think it's really more useful to start with a problem than uses. Carbon dioxide is used for carbonating beverages, for some food preparation things, and for enhancing oil recovery. But I think the point is that there are some reasons why you want to take CO2 out of the air that have to do with the fact that you got it out of the air. Our goal is not simply to supply carbon dioxide. In fact, there's no way we could beat the price of carbon dioxide you get from a well, because you can drill wells in the ground to carbon dioxide reservoirs and get it out very cheaply. We don't think we compete with that, but that's not the goal. The goal is to solve certain specific problems related to decarbonizing our energy system and to climate.
So can you go into the methodology? How do you pull carbon dioxide out of the air? Is it just like literally a filter that only that molecule goes through, or is it a chemical process?
Our process is an aqueous chemical process. Centerpiece is, so the core of our process is aqueous chemistry, where CO2 is a weak acid. We capture it in a strong base, a solution of potassium carbonate. Sorry, I'm tired. I haven't done this for a while.
Okay.
I feel like I don't give me a sense of what level of technical detail you want versus kind of commercial detail.
Well, essentially, what I'm hearing you say is that carbon dioxide can be encouraged to go into a liquid, and that pulls it out of the air and puts it into a liquid, and then maybe later it's
okay. I'll try this two-step basis. Yeah. So
sure.
The core of our process, chemically, carbon dioxide, which is a weak acid, is captured in a strong base, potassium hydroxide, and that's an aqueous solution, water-based solution. And the absolute core of getting cheap direct air capture is to have the contactor, the thing that first makes contact between the atmospheric air and whatever it is that's going to pull the CO2 out. That thing has to have low capital cost and low operating costs. And that's what we've done by adapting commercial air cooling technology you see for buildings and industries for just exchanging heat between hot water and the cool air. That technology we use for this purpose. That's, of course, just the first step. The second step is you need to do regeneration. You take the CO2 out of that solution and make the strong basic solution again so it can capture more CO2, and so you've got pure CO2 out. So the core of our process is a two-step process with a contactor and then a regeneration system.
Yeah, it seems like this would be good to put on the end of smokestacks, furnaces or refineries. So right there, you get a nice source of
a lot of carbon dioxide, and you can scrub it out before it even goes in the atmosphere, perhaps.
No. So that's conventional CO2 capture and storage. There are a set of technologies for capturing CO2 from power plants that have been existing for decades. We don't compete with those. It's quite a different set of technologies. It's a different engineering problem to capture from ambient air, where you're at 400 parts per million, to capture from a power plant where you're at 10%. It's always going to be cheaper to capture from a power plant in general, but it's a fundamentally different process design.
Yeah, you're dealing with much lower concentrations, so it makes it, I'm sure, a lot harder, and you have to process massive amounts of air, right?
Correct. So it's harder. It's not, I think it's much harder as you might think. I mean, so the advantages you have with direct air capture are that you always have the same air. The air is always there all the time. And so you can build a process tuned to do that. But the bottom line is this is not the same as capture from power plants. I think this whole conversation is sort of in the technical weeds and not dealing with what the goal is. So the way I see it, we're thinking our objectives deal with, you figure out how to answer the questions, but I feel like we're not kind of addressing what problem we're trying to solve.
Yeah, well, okay, so we'll get to that now. So, carbon dioxide concentrations, I mean, from what I know, they've gone up quite a bit. It's all tied to global warming, global climate change. So I would guess that a good result would be what? To get the ambient levels of carbon dioxide down from 400 parts per million to 200 or 250? Like, what's the overall goal of the technology?
Well, the central near-term objective for our technology is to enableize decarbonization of the heavy parts of the transportation sector. And the way to think about it is to make a bridge between cheap solar power and the high energy density fuels we need to power airplanes and other parts of the transportation sector that are hard to electrify. So stepping back, what we know is that solar power is getting ridiculously cheap. That's true. Not everywhere. Solar on rooftops isn't necessarily that cheap or cost effective, but large industrial solar photovoltaics in really great locations, high sun locations, are getting to produce energy at a cost that's cheaper, not just cheaper than any other low carbon energy, but getting to be cheaper than any other electric energy you can make on the planet. It's really stunning. And there seems to be no reason that cost trend won't continue. But getting cheap carbon-free solar power doesn't magically solve the world's energy problems. For one thing, it's only there during the day, it's only in some parts of the world, and we can't electrify everything. So for things that are already electrified, that can work well. I think we will electrify lots of light-duty vehicle transportation, but there are lots of the heavy parts of the transportation system where electrification will be harder, and there are other industrial uses where electrification is hard. So what you'd ideally like to have is a method for taking the energy that you got, the carbon-free energy you got from solar power, and turned it into a fuel, something that is transportable, storable, has high energy density, and ideally is compatible with existing infrastructures. And we have a way to make that fuel. That way is to take cheap solar power, combine it with CO2 you got from the atmosphere, and synthesize fuels that are chemically the same as existing fuels. That is, you can make gasoline or diesel, aviation kerosene, what have you, using processes that are called gas to liquids. The hard part is doing the CO2 capture from the air and going from solar power to hydrogen, and then hydrogen plus CO2 from the air to fuels. So that's the central goal, is this idea of what we call air to fuels, which is really about enabling us to indirectly make, if you like, stored solar fuels that could be used, say, for airplanes. And these fuels would be completely compatible with existing infrastructure. They'd be chemically the same fuel, but they don't come from the ground. They're not fossil fuels, and they allow you to have real carbon neutral transportation at large scale.
Well, on a net basis, you're capturing, X amount of carbon from the atmosphere. How much is going back into the atmosphere once the fuel is burned? Is there a zero net there, or is it net positive, net negative?
In terms of the actual carbon that's in the fuel, it's one for one. So when you burn fuels, all the carbon that's in the fuels goes into the air. But when you synthesize those fuels from the air, you're using carbon from the air. So it's one for one. You're basically just using the carbon as a carrier. The carbon is a package for the energy.
How much energy is required to do the direct air capture itself? Can solar be used to power that?
For sure, solar can be used for powering it, and the amount of energy depends on exactly the end product, but call it something like between 9 and 7 or so, or 6 gigajoules of energy per ton of CO2 delivered. But I think the important thing to say that number may not be instantly meaningful to your listeners, but that's actually comparatively small compared to the energy content of fuels. That's the key thing. So if you think about the total energy content need to make synthetic fuels, you've got the energy content need to actually put into the fuel, which is to go from CO2 back to hydrocarbons. And then you've got the added energy needed to do the CO2 capture from the air. And that added energy is pretty small, say 10 or 15%.
I think this is great. I mean, this would reduce reliance on extracting new fuels, new fossil fuels, and then it'll be a net zero contribution, essentially. You're pulling carbon out, it's going back once they're burned, but at least it doesn't add.
Yeah, so that's one of the central applications of direct air capture. And the other application is simply to do carbon removal, to get paid to remove CO2 from the atmosphere. So where the CO2 is captured and then put into deep geological storage. So those are the two basic applications. So direct air capture is a technology. The two primary applications we see are these synthetic fuels and large-scale removal.
Is there going to be a need for CO2 storage? Deep storage of it if this goes, if this scales up? Sounds like there wouldn't be.
If you want to do carbon removal, you need to have the storage. Yes. If you want to do air to fuels, there's no storage.
So at scale, how much of an impact do you think that this can make? How much of a demand is there for this?
Well, I think it's one of the few things I can think of that really could be scaled to meet a significant fraction of the total demand for the hard to decarbonize part of the liquid fuel economy. So I'm not claiming that our company will magically do that, but I think if you think about this as a sort of deep piece of the energy infrastructure of the planet, which could be, there'll be lots of competition to provide it, the idea that as one of the ways to decarbonize the hard to decarbonize parts of the energy system, we do cheap solar plus CO2 to fuels, I think there's no reason, there's no sort of fundamental scaling block to that not being, taking a big chunk of that energy demand. So the way to think about it is, total energy demand for transportation is a little less than a third of total energy. Of transportation, something like half or a little less or more, depending on where you are, is light-duty vehicles. I think most light-duty vehicles will get electrified, but I think the other part is harder to electrify. So I think of it as being something like a third or so of the total transportation use. Depends on how other things compete. So think of that as about 10% of total primary energy.
Yeah, so I was going to ask you, what is difficult to electrify? You said airplanes. What else in transportation?
Airplanes, heavy shipping, the heavy freight modes, some industrial equipment.
I guess the nice thing is those are concentrated users of fuel and concentrated emitters. So, a big freight liner would lend itself to having the direct carbon capture on it, but the fuel used to supply it, that you're getting from, the direct air capture. But it's better than having, millions and millions of individual little car engines.
No, but we're not talking about building the direct air capture machine on a ship or an airplane. We're talking about building the direct air capture machine where there's cheap solar power and where construction costs are low to make fuel, and then the fuel gets moved around with a regular fuel infrastructure, which is really cheap and easy.
But the cool thing is you're creating this fuel, you're gathering it from non-concentrated sources, you're concentrating it in the fuel. Then even when it gets burned, now you can rely on traditional carbon capture to grab it there instead of it. So it's a good system.
Well, you can't really rely on. I don't think conventional carbon capture would be useful for airplanes or ships.
Well,
conventional carbon capture really makes sense for large fixed sources like power plants or steel mills.
Well, at the very least, it would be a concentration of emissions over that of passenger vehicles, for instance.
I'm not really understanding. Yeah.
I understand how you play into the process, and it all makes sense. I'm just remarking that it works well with the existing systems. So what are the fuels that you can create with the direct air capture?
Well, that's a great question, and the answer is that turns out to be the easy part. The hard part is getting hydrogen at low enough cost and getting CO2 from the air at low enough cost. Then you do something called gas to liquids technologies, which are similar technologies that are used nowadays to turn natural gas into liquids. And these technologies really exist at large scale already. There's something like 150,000 barrels a day globally of gas to liquids technology. And once you do gas to liquids, you make something, depending on how you do it, at least one pathway, you make what's called Fischer-Tropsch liquids. And then in a refinery, you can make those into really any product you want. So you can make them into gasoline in principle, or into aviation kerosene, the thing you need for airplanes, or diesel. In practice, there's some complex details in like which pathway you choose, and there's other pathways like methanol to gasoline. But the important thing to say is all that is existing industrial technology, which we do not have to invent or bring to market. It's already proven at full industrial scale. What we're doing is providing different inputs to that technology.
Gotcha. Okay. So what are some of the stumbling blocks to doing this? Is it what kind of conditions do you need? Can you locate your direct air capture anywhere? Or are there certain climates or conditions that it's more beneficial?
Yeah, so no, we can't. So in principle, direct air capture means your independent location. Of course, any practical air capture technology is going to have places where it works better and less well. So, we work. We need a fair amount of water. We need land. We need energy. We don't want to be in super dry conditions. So there are a range of places that work well for us. We don't work well if we're a long way below freezing. So there's a very wide range of places that our technology is applicable, but not everywhere. But there are other capture technologies beyond ours. I think that the main point is, at least as we see the market, the hard part of the market is not finding locations that could work. The hard part of the market are, the normal thing of getting a new business started. You need to, finance initial large plants, and for that you need offtake agreements and financing and regulatory structure that makes sense, and so on.
Okay, well, very good. Where are you at with this? Do you have any number of plants operating, or is this more bench scale? Like how far along is this?
In between those two. So it's much bigger than bench scale. There's been a large pilot operating at Squamish, British Columbia for quite a few years. The company's now like a 70-person or so company, and we are now in the middle of negotiations looking to finance the first large plants. These would be plants that would be, of order 500,000 tons a year of CO2. So this is plants that cost a good fraction of $1 billion. So we're in the middle of trying to do that financing now, where we have several different kind of potential sites and off-takers and regimes into which those plants might make sense.
Would you want to or need to co-locate with a gigantic solar farm, or does that not matter?
It matters for air to fuels. It doesn't have to be exactly co-located, and wind power is also relevant. I think solar is more important in the long run, but wind power matters as well. So yes, absolutely, we've been working with solar and wind suppliers, or even companies that do both, and to provide you contracts that have very high availability. So yes is the answer. You don't necessarily have to be co-located, though. For some regulatory regimes like California, there is some requirement for co-location, and we are definitely looking at that.
Okay, very good. Well, what's the expectation for the next 3 to 5 years? Are you going to have the plant you're talking about up and running, or is it going to take longer? Or?
It'll take longer than that. Any big industrial plant like this takes at least 3 years from the actual starting gun, when all the financing is done and you're finished the core of the full project engineering phase. We're right now have financing for what's called the front end engineering and design study. So that's begun, which is very exciting. That was announced sometime over the summer. But I think there's no way we have a full commercial plant operating in 3 years. I think it is my goal would be to see the financing in place for a commercial plant next year, so we can really move directly from the front-end engineering design study into the beginning of the engineering procurement construction phase.
So what's more realistic until the plant opens its doors and starts running?
I'd say about 5 years.
Okay. And then do you think that
could be a little? I mean, yeah. So that was a bit. I'd say round numbers about 5 years. It could be more like 4. Could be a little longer. That's That's the kind of timescale these big industrial plants take.
Well, once the first one's operating, is that going to make it a lot? Will that fast track other plants and get it out there?
Well, for sure. And I don't think it's just that we wait all the way until the first plant is operating, because there's some intermediate, smaller things that will be operating. And also, I think once we have successfully financed and gone into the full construction engineering of a large plant, probably that will already reduce risks enough in the eyes of other investors that will then be able to finance other plants. So that's what we'd hope to do.
And which are there countries that are showing interest, or is it just industry players, or who really wants this?
So there's an amazing amount of interest now in direct air capture and in carbon removal. I'd say, in some sense, the interest is driven by, ultimately all by the need to reduce CO2 emissions, to reduce climate risks. And that need is appearing in different regulatory regimes in different ways. But so in the United States, things like the California Low Carbon Fuel Standard, which has an explicit regulation on the what's called the well-to-wheels emissions of fuels, and they basically added on top of that a way that the California Low Carbon Fuel Standard (LCFS) price can get applied directly to direct air capture removals. So that's one of the most important ones. There's a set of things called 45Q in the U.S. that also provide a explicit tax incentive with an extra incentive for direct air capture to pure storage, which is something we're pursuing. But that's just the U.S. Similarly, there's a low carbon fuel standard that's under evolution in Canada. There's much discussion about making this a kind of UK priority. There's European discussions. There's a fair amount happening globally about the governments finding ways to produce regulations that will incent these kind of, not specifically our company, but find ways that will incent these kind of carbon removal or ultra low carbon fuel systems.
Okay. Well, very good. Well, what's the best way for people to get in touch, to ask questions or ask for more info?
So to go to the company website, carbonatsharing.com, and there's lots of background information, white papers, videos, and so on, and contact info.
Okay. Well, very good. Well, David, thank you for coming on the podcast. I appreciate it.
Great. Thanks a whole lot. Take care. Bye-bye.
You're listening to the Future Tech Podcast with Richard Jacobs. Future technologies such as artificial intelligence, stem cells, 3D printing, gene editing, Bitcoin, blockchain, the microbiome, quantum computing, virtual reality, and exploring space are much closer than you might think. In fact, many early versions of these technologies are in play right now, and the companies that are using these technologies are the focus of this podcast. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a thorny medical problem. Remember, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you've enjoyed the podcast, please listen, subscribe, like, and tell your friends about it. Thank you.